was a dark and stormy night. The prototype had arrived. The team was scared. No one wanted to even open the box. They knew the danger. They had battled this monster before, and they knew firsthand the kind of horror that could await them inside. All right, maybe it's not all that bad. We all know that the prototyping phase of your design, especially your embedded design, can be a pretty scary process. Everybody has a story. You thought you were done, the board comes back, and oh, not really. Trip to Maui rescheduled, and I'm sleeping in the den for the next week. Sure, you could try to do all of the prototype verification in-house by yourself, verifying your hardware against what you thought your design was supposed to do, and trying to figure out why the heck your third board doesn't work at all. Or you could try a new approach to functional prototype verification and get that Maui trip back on the calendar. Hi, I'm Amelia Dalton, host of Chalk Talk, and today my guest is Bob Potok. Bob and I are going to chat about how you can save yourself all that headache at prototype time. How Casio's VTOS, that's Verification and Test Operating System, can solve all of your embedded design prototyping problems and get you back on that flight to Maui and back in your team's good graces. Before we get started, remember to click on that Download Now button below your player. There you can download a free white paper entitled Introducing VTOS for Embedded Hardware Verification. Thank you so much for joining me today, Bob.
Thanks, Amelia. I'm happy to be here. Today we want to talk about embedded hardware design verification, and that process begins when the prototype arrives. And this could be one of the most exciting times of the design process, as well as one of the most stressful. And we want to talk about a design verification process that will help engineering teams find design errors faster and improve overall design quality.
Okay, so Bob, my prototype is in hand. How exactly does this fit into my hardware lifecycle?
Well, the hardware lifecycle has three primary stages: design creation, production test, and the actual usage in the field. The design creation process is fairly well understood, and there's a pretty good toolkit to get that job done. Similar with the production test floor. We have in-circuit testing, boundary scan, functional test, and we also have some power on self-test for the field. The big gap is when the prototype arrives, and that's the process we call design verification.
So, Bob, why is the prototype so challenging?
Well, as I mentioned, it's one of the most exciting times of the design process because this is where the rubber hits the road.
Okay.
I'm taking my prototype out of the box. The challenge is to get it to the software team as quickly as I can so that they can start software development. The challenge here is that the software team wants a quality design.
Sure.
And they want it quickly. So I've got a lot of pressure, and so I have stress. And the real challenge is when you consider what a prototype is. A prototype is comprised of a new schematic, a new printed circuit board layout, new components, new assembly, all coming together for the first time. Simulation is great, but simulation can only go so far. This is the prototype. And the challenge is to have an effective design verification process so that I can release a quality board to the software team as fast as I can.
Okay. So is this applicable to all embedded designs?
It is. The embedded design market is extremely broad. In fact, it's over $1 trillion market. It encompasses consumer products, automotive, communication, industrial products. And the components that are going into these embedded designs today are becoming more and more complicated, and thus increasing the test complexity.
Sure.
So when we look at an embedded design, let's start with a memory. There's at least 4 different types of memory that can go into an embedded design with all different test strategies. When we look at buses, we have PCI, we have serial I/O, we have USB, we have CAN, we have I2C, we have SATA. A lot of buses with a lot of different peripherals hanging on them. We also have image, audio, and video type peripherals. This is where a lot of the complexity comes from. We have very high density displays, we have touch screens, we have cameras, we have audio systems, both in recording and production. And finally, we have miscellaneous parts, real-time clocks, FPGAs, we have GPIO, we have Ethernet, Wi-Fi. So when you look at the aggregate of all these different types of components, and they're changing on a regular basis, you can see how the test complexity is growing quickly.
Absolutely.
And there's one more thing that's affecting design complexity. PCB technology with high density interconnect is limiting the test access points. So now debugging these boards is becoming more and more difficult as well.
Okay, Bob, so how do most people test their embedded designs today?
Well, Amelia, there's two common test strategies. One is test program development.
Okay.
And to do that well, it's a 1 to 2 year investment.
Wow, goodness.
It is significant. And the downside of that is typically those investments are project specific, meaning there's little reuse project to project. A second approach is actually using the application OS. Now that has a different set of problems. First, you have to realize that the application OS has just been ported to the prototype hardware. So now I have a situation where I have new software testing new hardware.
I see, okay.
And that is not the best situation. Another consideration about the application OS is that the application OS is built for hardware abstraction, which means it's putting you a long way from the hardware. Between you and the hardware is a large software stack, and that's not desirable as well. So the outcome is generally marginal test tools and a marginal test process that has limited test coverage, limited margin testing, and poor fault isolation tools.
All right, this makes sense, but a lot of things can go wrong here, right?
Absolutely, Amelia. The biggest fear is not being able to find or isolate design problems. So a board could be released to the software team with unstable RAM, missing pull-ups, bad clocks, unstable MIPI DSI interfaces. These are all real problems that we found in the past. Those problems lead to unnecessary board spins, which lead to unexplained crashes. And this is one of the biggest fears, where the hardware team can't isolate the problem, the software team can't isolate the problem, and that's going to lead to finger pointing.
And no one likes that, certainly.
And then what happens next? Weeks of delay. And then the tension starts growing, the stress increases, and then we have a major problem.
I don't mean to alarm you, Bob, but I think my hair's on fire. Other than that whole hair on fire thing, I think most of us have experienced some part of this. There has got to be a better way, though, right?
There is a better approach utilizing a verification and test OS called VTOS.
Okay.
And VTOS is a special purpose operating system for hardware verification. It gives the engineering team downloading booting options with JTAG or U-Boot. It provides OS services that are verification focused, like scripting and file transfer and tracing for the purpose of debug. It also gives you a verification console that gives you great visibility and control into the hardware. So you can read and write registers in memory, you can change test parameters, you can loop on tests, and finally, it comes with a great functional test library. And what's really important about this is the hierarchical structure. At the bottom are commands, methods are built upon commands, tests built upon methods, suites built upon tests. It's a great architecture for a functional test library.
Okay, this sounds pretty cool. How does this fit into my design process, though?
Well, now that you have VTOS, which is the foundation, I can implement a verification process.
Okay.
And there are two key milestones in that verification process. One is what we call design correctness. The second is called production readiness.
Okay.
So imagine you're taking your prototype board out of the box.
All right.
There's a sequence of activities that you want to go through before you can meet the design correctness milestone. Initially, you'll do some power checks on the board, check some clocks. Then you're going to load and boot VTOS. From there, you'll run memory tests, peripheral tests, performance tests. All along the way, you want to make sure you have a great debug and fault isolation capability.
Okay.
Once we pass all those functional tests, we can declare the design correctness milestone achieved and release the board to software.
Okay.
But at that point, we're not ready for a production release. Now we want to test for production readiness. And that means establishing a functional baseline, doing some margin testing, doing some change testing, and finally release to production.
Okay, so you've been talking a lot about design correctness, but that can mean a lot of things. Can you walk us through what you mean exactly by that?
Sure. First of all, we're trying to identify design problems. They can be both logical in the schematic and they could be physical in terms of the printed circuit board layout.
Sure.
The best approach for fault identification is the usage of functional tests.
Okay.
So we'll apply a battery of tests to that prototype hardware with the goal of one board passing all those tests.
Ah, okay.
Let me give you an example. So here's a schematic. Let's assume that the schematic is logically correct, and we're going to implement 2 printed circuit boards based on that schematic. The boards will have different placement, different routing, and different timing margins. When I apply this battery of functional tests, one board may fail and one board may pass. The board that passes we could declare as being design correct.
Ah, okay.
Okay, so there's a clear example between being logically correct and being physically correct.
All right, my design is all correct now, and I'm ready for production, right?
Not so fast.
Ah,
What we want to do is make sure the design is production ready, and having one board pass all the functional tests is not enough. So the next step is establishing a quality baseline.
okay.
At this point, we want to establish a quality baseline test. And here we're trying to identify implementation problems and margin problems because we already know the design is correct. We also want to do some margin testing, and I'll talk more about that. So here's a great example. Let's just say your first prototype run consisted of 4 boards.
Okay.
We want to take those 4 boards and we are going to apply a baseline functional test. Some of the boards will pass, some of the boards will fail. Let's assume that 3 out of the 4 boards passed our baseline test.
Okay.
The one board that failed because of implementation or margin errors. Remember, the design is correct.
Okay, yes.
So the question is, am I ready to release to manufacturing? Obviously, I'll do some investigation as to why the board failed. And the failure could be because of assembly problems, or it could be a signal integrity problem requiring a board spin. But at the end of the day, after doing this baseline test, you'll have a very good idea of the quality of the board and its readiness for production.
Gotcha. Okay, so Bob, a lot of our designs have second source parts, and sometimes equivalent parts are not really equivalent. Is there anything you can do to help us with that?
That brings up another area of testing that we call change testing.
Okay.
And the objective of change testing is to detect functional differences. So we're going to be looking for deltas in your design utilizing a baseline test. What's really key here is test consistency. Apples to apples. I want to be able to quickly and efficiently run the same test sequence to look for differences.
Okay.
So one example is testing for design fixes. So I have board spin 1, board spin 2. I fixed 3 problems when I went to board spin 2. Did I really fix the problems? And also, did I introduce any new problems? The best way to test for that is through a functional test battery. I'm also going to look at second source parts, going back to your question, as well as counterfeit part detection. As you said, the equivalent parts might be declared equivalent, but on a functional basis, those designs may not be equivalent within your design. So here's an example. Let's say we have design spin 1
Okay.
and we have design spin 2, and we made a number of changes. In design spin 2, we also want to apply some second source components. We've added some new variables. What we'll do is we will apply our functional baseline test to both boards. Based on those results, we're going to determine if those 2 designs are functionally equivalent, and we will identify differences if they exist on a functional basis. I can't emphasize enough the importance of using functional testing to highlight board differences.
That makes absolute sense. So, Bob, we've been talking about VTOS, but I'm not exactly sure what it is.
Well, let me show you a block diagram of VTOS.
Oh, right.
It's very straightforward. There's essentially 3 layers that we're looking at. The first being the hardware abstraction layer, and that is configurable using a device tree, which I'm going to talk much more about in a minute.
Okay.
The next layer up is the functional test layer. The functional tests are actually incorporated inside of VTOS. And Amelia, you can add to those tests, you can modify those tests, you can change the test sequences. They're very flexible in that sense.
Very nice.
At the user level, we have a command shell where you can actually do scripting for test modification and creation. You could do file transfer, as well as device programming. So it's a very simple, very straightforward architecture, but it meets the objective of direct hardware access, putting that hardware engineer, you, very close to the hardware.
Very cool. Okay, so you're calling this an operating system. I'm familiar with Linux. How does VTOS compare with Linux?
Okay, so here's a great diagram to show some of the important differences between the two operating systems. Let's start with the idea of a dual boot. So let's say I have my prototype board and I have U-boot running on my board. At this point, I can either boot VTOS for doing hardware verification, or I can boot Linux, for example, as my application OS to verify the applications.
I see, okay.
Now, when I compare these two operating systems, they differ at the hardware access methodology. They're fundamentally different. VTOS uses a direct hardware access methodology. The application OS is really built for hardware abstraction. Fundamentally different objectives. When I look at the size of the operating systems, VTOS is less than 6 megabytes, Linux on the order of 100 megabytes.
Wow, okay.
And that size is reflected in their boot times. VTOS, less than 10 seconds, which is great for iterative debug processes. Linux, 40 to 60 seconds. One of the fundamental differences, functional tests, that we've been talking about all along. VTOS comes with a functional test library. Linux or an application OS typically does not. Device drivers are another area of difference. With VTOS, the device drivers tend to be very simple. It's a very light OS. One of the cool things about VTOS is that I can actually create a device driver with scripting.
Wow, okay.
I don't have to get into any programming.
Very cool.
On the other hand, device drivers in an application OS tend to be very complicated. Device programming, when we talk about FPGAs or E-squared proms or Flash, again in VTOS, very simple, very direct, not so straightforward in the application OS. When we look at peeking and poking at memory addresses, VTOS is very straightforward and it can be done through the command line. On the other hand, with the application OS, it's generally a more complex problem because the applications are running from the user space.
Okay, Bob, we've talked a lot about functional testing, but what do you test?
Great question. The way our functional tests are organized are around device categories. So
Okay.
for instance, we have memory tests, we have display and camera tests, we have Ethernet tests, we have tests that will cover the different types of buses, I2C, SPI, PCI. We have tests that would cover sensors, power chips, and we also have different types of memory, flash, E-squared PROM, eMMC, and so forth. What's critical in the functional test strategy is that you get the CPU and the memory thoroughly tested before you move on to the peripherals. Remember the design correctness process?
Yeah.
Memory first. So once you've gotten the memory tested and the CPU and you feel very comfortable, then you can expand the circle of testing to incorporate these different devices. Now, let me give you a detailed look at what the functional test structure looks like. Remember that I mentioned that the structure is hierarchical.
Yeah.
So at the bottom, we have low-level commands. Read and write bytes. The test methods are built upon those low-level commands. And again, the diagnostic tests are built upon those test methods. So let's look at a couple of the diagnostic tests.
Okay.
We have an address bus test. We do a burst access test. We do both byte and word access tests. Then we do something called a bus noise test, which is relatively unique. We can do data patterns, walking ones, walking zeros. The user can change those, as well as an important test for simultaneous switching output. What's important here is that we're not just doing superficial memory testing. Superficial memory testing is not going to uncover instability problems in your RAM design. This type of test coverage will. Now, the purpose of a suite is to actually build more of a profiled test sequence,
Ah, okay.
whether it be performance, whether I just want a quick test or I want a comprehensive test. And you could actually build different test suites, possibly to debug a memory problem that you found, whether it be with your flash, could be an MMC problem, could be an SDRAM problem. You can localize it and then iterate on that test suite.
Ah, okay. Okay, Bob, my prototype has arrived. I pull it out of the box. How do I get VTOS on my board?
That's a great question, and we get it a lot when you talk about an operating system. Getting VTOS on your board is extremely straightforward, and we can actually be running tests in 30 minutes.
Wow.
It's a 3-step process. Step 1, we're going to configure the VTOS. This is a configuration step that I'm going to talk about a little bit more. Let's be clear, it is not a porting step.
Okay.
The second step is actually downloading the VTOS onto your board using JTAG or U-Boot or any bootloader that you choose. And finally, the third step, you're actually running tests inside Integration Workbench, which is our user console. And then we can start executing command line tests, we can execute scripts, we do logging, both on commands as well as the output of the tests.
All right, Bob, I'm a hardware girl, and I'm a bit apprehensive about this whole porting thing. Are we really configuring, or are we porting?
Amelia, we are configuring.
Phew.
I know, no fear, no porting, no programming required. And the way it's done is through the configuration of a device tree using a product called VTOS Builder.
Okay.
So the first thing you would do is select a processor family. And in this case, this is a Freescale Core IQ P2 processor package. This could have easily been a Texas Instruments OMAP 3, OMAP 4. It could have been a Freescale IMX 6.
Okay.
The next step is to how do I start the configuration process? Well, you have two choices. You can start with a reference board, which are typically offered as part of the processor family, or you can start with a specific SoC. In this case, it could be a Core IQ P2020 or a Core IQ P2040. We also give you some example peripherals that you could literally drop and drag onto your board.
Very nice.
And finally, we'll give you a little area so that you can save your own custom trees. You may find it very convenient to create multiple device trees for different purposes.
That makes sense. So this is how you configure it, but Bob, how do I add a component?
Well, let me show you a quick example. What I want to do is add a real-time clock to the I2C bus.
Okay.
So we've seeded the tree with an SoC, and the tree now that we're going to be working with is on the right side, or the right panel. I want to take a real-time clock from my peripheral library, and I will literally drag it onto the I2C bus. Once it's on the bus, I'll configure the device driver parameters using this dialog. So for instance, I can set the address of the real-time clock. Once I've got it configured, the next step is to configure the VTOS. And the VTOS configuration starts with what we call a raw VTOS.
Okay.
And then we combine that with the device tree that you just configured, and the output is a VTOS image ready to be downloaded and executed on your prototype. This whole process should take less than 30 minutes.
Wow, all right. So I've got VTOS and I've got it on my board. Let's take this baby out for a spin. What can I do?
All right. VTOS is a complete test environment. It starts with local and remote access. On the image to the right, you could see I can be connected with a serial bus, a USB, or an Ethernet. So I can be debugging my prototype while I'm sitting in my office and the prototype's in the lab.
Very nice.
I have a fast boot time because we all know debugging a board is a highly iterative process. We don't want to waste time waiting for boot cycles.
Absolutely.
We have the functional test suite that we discussed earlier. We also have a command line that's ready to give you peek and poke capabilities into registers, into memory. And what's really powerful is we have a trace capability that could be stored into a log file. So Amelia, you can set the trace level from 1 to 6. At trace level 6, you're going to see every register read and write and every memory read and write that the functional test or your script executes. It's
okay.
a great debugging tool. You also have interpretive scripting, and this is really important because there's no compilation required. You can modify a script and have VTOS run it in a matter of seconds. You can customize test sequences, you can modify test parameters, and you can all do that within a scripting language. We also have the ability to do file transfer and flashing. So a great example for file transfer is you might want to download a new version of VTOS to flash so that now you can boot it from U-Boot as opposed to doing a download through JTAG.
Okay.
Very straightforward. And also as part of that file transfer is I can actually download an FPGA bit file and program the FPGA directly through VTOS.
Very cool.
As well as doing the programming, I can actually create an FPGA functional test using scripting as well. So you can see the power of scripting is really important to the hardware engineer because they may not be interested in writing a lot of C-based programs to get these things done.
That makes sense. So Bob, let's get down to some nitty and gritty details here. How do I really drive this thing?
Well, the user is going to be working with Integration Workbench, and let's give you a quick overview of that.
Great.
First, we start with the panel on the left is the functional test command tree. This is literally all the functional tests that are available to you. And they're organized around device type. So as you look through this left panel, you can see cameras, you could see CPU, you could see E-squared proms, you can see Ethernet, and so forth. We also have a DUT selection capability. What's really cool is Integration Workbench can talk to 8 prototype boards simultaneously. And this is really powerful when you're trying to debug and compare and contrast prototypes.
Okay.
You also have the ability to just simply click to run the tests in the left panel. You get the test results in the large window, and in this case we ran a performance test on our memory. It tells us the range of the test, that it was a 32-bit access, and the actual throughput time. You have the command line at the bottom that we talked about earlier, peek and poking at registers in memory, commands, scripts, and what's really cool, and I mentioned this earlier, you can write a script in Notepad or Notepad++ and literally drag and drop it on the command line, and you can now execute that script. It's a highly iterative process for debugging hardware as well as debugging or expanding your script.
Very cool. So this sounds like a great design verification solution, but it seems like it might be a good fit on the production floor as well.
It can, and let's go back to that hardware lifecycle slide we looked at earlier. This presentation has really been focused on design verification when the prototype hardware arrives, and we're using VTOS as the foundation for that hardware verification. But that VTOS can easily move into the production test phase and fulfill the functional test requirement. And that is a seamless and easy transition for an organization to take advantage of VTOS on the production test floor. Another interesting application of VTOS is actually shipping VTOS with the product. It gives the company or gives you the opportunity to run field diagnostics or even power up self-test in the field to eliminate the hardware variable when there is a problem.
Very cool.
So VTOS gives you a lot of flexibility across the hardware lifecycle.
Wow, okay. So Bob, we've covered quite a bit in this presentation. Let's review some of the stuff we talked about.
Okay, Amelia, let me leave you with a couple points. First, VTOS is built for board-based design verification and test. It is a special purpose operating system, and it requires no porting.
Very good. Phew.
The purpose is really to find design errors faster and improve your overall design quality. It's an easy transition to the production test floor, so you get a lot of leverage from engineering to production. And overall, it can save you up to 75% in test development costs.
Well, I think that's all I have time for today. Thank you so much for joining me today, Bob. It was a pleasure speaking with you.
Thanks, Amelia. I had a great time.
And before we go, don't forget to click that Download Now button below your player. There you can download a free white paper entitled Introducing VTOS for Embedded Hardware Verification. For Chalk Talk, I'm Amelia Dalton. For more Chalk Talks, check out the on-demand section of eejournal.com.